Hi, my name is Fedyanin. I am a senior research fellow in Laboratory of Nano-Optics and Plasmonics of the Moscow Institute of Physics and Technology. Until recently, epitaxial quantum dots were supposed to be the most promising candidate for true single-photon sources on demand. However, they have serious limitations, which make it difficult to implement them in practical devices. One of the most critical limitations is a low operation temperature required to achieve a high count rate and a narrow emission spectrum. Color centers in diamond can be used to overcome this limitation. At room temperature under optical pumping, the emission rate can be as high as 10 to the power 6 counts per second, and the spectrum line width is as small as 6 nanometers at the same time. But the problem is that optical pumping is not suitable for most practical applications, since the energy efficiency of optical pumping is extremely low, and one needs an external, bulky, high-power optical source to pump the nanostructure. For these reasons, a compact and energy-efficient electrical pumping scheme should be developed. Fortunately, diamond is a semiconductor, and color centers can be pumped electrically using a small piece of diamond and a conventional battery. However, the observed emission rate was as low as 10 to the power 4 counts per second. This number is much lower than that for electrically pumped epitaxial quantum dots at low temperatures and optically pumped color centers in diamond at room temperature. Since the physics behind the electroluminescence process was not known, it was not clear to what extent the photon emission rate can be increased and whether color centers in diamond can compete with electrically pumped epitaxial quantum dots and other single photon sources. In this work, we reveal the electroluminescence mechanism and present for the first time the theoretical framework to study single photon emission from color centers in diamond under electrical pumping. Moreover, we demonstrate that it's possible to design an ultra-bright, electrically driven single photon source based on color centers in diamond. We show that the emission rate can be as high as 10 to the power 9 counts per second at temperatures above room temperature. Color center in diamond is an atomic-like system, and this means that under optical pumping, basically, there is no interaction between the color center and diamond itself, of course, except interaction with phonons, which can only affect the emission spectrum. If we want to pump the color center electrically, the situation is fundamentally different, because the color center has to interact with diamond by accepting and releasing electrons and holes. It's very difficult to treat this interaction. However, we succeeded to do this by introducing a relatively simple three-stage model. This process of electron and hole capture are accompanied with structural transformations of the color center. This means that accepting or releasing an electron, the color center changes its energy level structure and consequently the emission properties. For this reason, we have to deal with different charge states of the color center in a single cycle of the electroluminescence process. Our theory gives a possibility to predict the photon emission rate from the electrically pumped color center in a diamond diode. Moreover, we have shown that the previously reported low emission rates are due to the strong donor compensate effects in the N-type diamond, and using state-of-the-art doping techniques, it is possible to increase the photon emission rate of up to 10 to the power 6 photons per second. But what is much more interesting is that the photon emission rate increases as the temperature of the single photon emitting diode increases. For example, at 200 degrees Celsius, the photon emission rate is 3 orders of magnitude greater than at room temperature and can be as high as 10 to the power 9 counts per second. This is one of the few optoelectronic devices which should be heated up in order to improve their performance. Usually, characteristics of electronic or optical devices, on the contrary, decrease as temperature increases. Our findings demonstrate that electrically driven single photon sources on diamond can be very bright. They can operate at room and high temperatures and are very perspective for different applications ranging from fundamental quantum optics to secure optical communications based on quantum cryptography.